Section 4 of the Chapter 1 is Grüneisen parameter. When the temperature T increases, the pressure P increases if the volume V is kept constant. This pressure increase is referred to as the thermal pressure, or more frequently, the rate of the pressure increase to the temperature increase at constant volume is referred to as the thermal pressure. Therefore, mathematically, the thermal pressure is expressed as the partial derivative of pressure P with respect to the temperature T at constant volume. From the chain rule, this quantity is equal to minus the partial derivative of volume V with respect to the temperature T at constant pressure P times the partial derivative of the pressure P with respect to volume V at constant temperature. The former factor is multiplied by 1 over V, and the latter factor is multiplied by minus V. Then the former part is the definition of thermal expansivity, and the latter factor is the definition of the isothermal bulk modulus Kt. Therefore, the thermal pressure is the product of the thermal expansivity and the isothermal bulk modulus. Equation 1.4.1. This diagram shows the thermal pressure, namely the product of the thermal expansivity alpha and the isothermal bulk modulus Kt of Pericles and forsterite with increasing temperature at ambient pressure P0. As you can see, at temperatures above 500 kelvins, the thermal pressure of forsterite and Pericles are relatively constant. This is because the cancellation of the increase in thermal expansivity alpha with increasing temperature T and the decrease in the isothermal bulk modulus Kt with increasing temperature T. In this slide, we define the Grüneisen parameters. The physical meaning of the Grüneisen parameter gamma is at what rate the pressure P increases with increasing density of the internal energy E when the volume V is kept constant. Why do we not say not simply the internal energy, but the density of the internal energy is that the internal energy E is the extensive variable, namely its magnitude depends on the size of the matter. If we define the Grüneisen parameter gamma simply based on the internal energy E, the Grüneisen parameter gamma is size dependent and cannot be a physical property of metals. According to the concept mentioned above, the definition of the Grüneisen parameter gamma is given as the product of the volume V with the partial derivative of pressure P with respect to the internal energy E at constant volume V, which is nearly equal to the pressure increase divided by energy increase per volume. The equation 1.4.2. In the section 1.2, we defined the thermodynamic Grüneisen parameter gamma Th. The thermodynamic Grüneisen parameter gamma Th is defined as the thermal expansivity times the isothermal bulk modulus Kt and volume V divided by the isocaloric heat capacity Cv. Equation 1.2.12. Then an open question is where the Grüneisen parameter gamma and the thermodynamic Grüneisen parameter gamma Th are identical or not. Here I show the equivalency of the Grüneisen parameter gamma and the thermodynamic Grüneisen parameter gamma Th. The right side of the equation 1.4.2 without the volume V is the partial derivative of the pressure P with respect to the internal energy E at the constant volume of V, which is equal to the partial derivative of the pressure P with respect to the temperature T at constant volume V times the partial derivative of the temperature T with respect to the internal energy E at constant volume V. This formula is obtained by the derivative of the composite function, namely if y equals the function of f, which is the function g of the function x, the derivative of the function f with respect to the parameter x is equal to the derivative of a function f with respect to the function g times the derivative of function g with respect to x. Then this factor, the partial derivative of the temperature with respect to the internal energy at constant volume V, is the reciprocal, the partial derivative of the internal energy E with respect to the temperature T at constant volume V. Therefore, this formula is equal to the partial derivative of pressure P with respect to the temperature T at constant volume V divided by the partial derivative of the internal energy E with respect to the temperature T at constant volume V. Then the denominator of the equation 1.4.3 is a definition of the isocaloric heat capacity Cv. This one, equation 1.2.1. We have already seen it in the chapter 2. And the equation 1.4.1, the thermal pressure, the partial derivative of the pressure P with respect to the temperature T at constant volume V is equal to the thermal expansivity times the isothermal bulk modulus Kt. Therefore, we substitute this equation into 1.4.3. We substituting the equation 1.4.1 and 1.4.3 and 1.2.1 into 1.4.2, we have the thermodynamic Grüneisen parameter gamma is equal to the volume V times the partial derivative of pressure with respect to the internal energy V at constant volume V is equal to volume times alpha kT divided by the isochloric heat capacity CV. And this is the definition of the Grüneisen thermodynamic Grüneisen parameter gamma TH, equation 1.4.4. Therefore, the Grüneisen parameter gamma and the isothermal Grüneisen parameter gamma TH are equivalent. This slide explains the meaning of the Grüneisen parameter. The Grüneisen parameter gamma is the indicator showing the rate of the pressure increase by the internal energy density increase at constant volume. Then let us divide the Grüneisen parameter into two parts, alpha kT and V over CV. Alpha is the matter attempts to increase volume by temperature increase, and kT, the isothermal bulk modulus, is the efforts for the volume increase is converted to the pressure increase. Therefore, alpha kT is again the pressure increase by temperature increase, or the rate of the pressure increase to the temperature increase. On the other hand, the isochloric heat capacity CV is energy increase by temperature increase, and CV over V is energy density increase by temperature increase. Therefore, V over CV is equal to the temperature increase by the internal energy density increase. If the alpha kT is higher, the pressure increase by a given temperature increase becomes larger. Therefore, the isothermal thermodynamic Grüneisen parameter increase proportional to the thermal pressure alpha kT. And if the V over CV is larger, then temperature increase by a given internal energy increase becomes larger. Therefore, the pressure increase by given temperature increase become larger by a given energy density increase. Therefore, the thermodynamic Grüneisen parameter increases with increasing V over CV. This slide demonstrates the relative constancy of the Grüneisen parameter. First, let us see the thermal expansivity alpha. In this diagram, the red curve is the thermal expansivity of a Pericles, and light green is the thermal expansivity of forced light. The orange is the Grüneisen parameter of Pericles, and blue-green is the Grüneisen parameter of forced light. As you can see, the thermal expansivity increases with increasing temperature, especially low pressure, but even at high temperatures, thermal expansivity increases with increasing temperature. Then the Grüneisen parameter, which can be divided into the alpha kt and Cv part. As we have already seen, the alpha kt, the thermal pressure, is nearly constant at high temperatures, and the isochoric heat capacity Cv is also nearly constant at high temperatures. Therefore, as a result, the Grüneisen parameter gamma is also nearly constant at high temperatures. On the other hand, the Grüneisen parameter is not constant at lower temperatures because the thermal expansivity alpha and kT varies differently at low temperatures. Then finally, let us see the factor 1 plus alpha gamma t. The factor 1 plus alpha gamma t is the ratio of the adiabatic bulk modulus to the isothermal bulk modulus, and also the ratio of the baric heat capacity to the isochoric heat capacity. Then temperature dependence of the 1 plus alpha gamma t is of course positive because the alpha gamma t are all positive value, and the alpha increase with increasing temperature, and gamma is independent from the temperature. Therefore, the factor 1 plus alpha gamma t increases with increasing temperature. So this diagram shows the factor alpha 1 plus alpha gamma t of Pericles and forsterite. In the mental at low temperatures, the alpha gamma t is nearly equal to unity. Therefore, Cp and Cv, or Ks and Kt, are equal at low temperatures. However, at mental temperature, for example 1500 kelvins, the factor 1 plus alpha gamma t exceeds 1.1. Therefore, the ratio of the Cp and Cv, or Ks and Kt, are more than 10% different at mantle temperature. So this is the end of the section 4 of the chapter 1, Grüneisen parameter.